Hello everyone, welcome to this section which is about generative adversarial networks. In this section, we are going to explain about one of the most important fields, unsupervised learning, which is improving every day. We will also try to solve an experiment with GANS to be prepared for the future implementation. In this video, we are going to explain about the basics of the generative adversarial networks and their applications. We actually want to know how GANS really work and what is the logic behind them. Generative adversarial networks, or GANs, are deep neural net architectures comprised of two nets pitting one against the other. That's the reason why they are called adversarial networks. GANs were introduced in a paper by Ian Goodfellow and other researchers at the University of Montreal in 2014. GANs' potential is huge because they can learn to mimic any distribution of data. GANs belong to generative models and algorithms. Generative models try to learn the distribution of the input P of X and thus can be thought of as a type of unsupervised learning algorithms. GANs are used to generate or model high-dimensional data. Generative models can create data and can also be used for the classification and regression like the discriminative counterparts. Generative models have more information about the data since they both create the input data and solve models by predicting the output. So what are the pros and cons of the GANs? GANs generate the sharpest images and are easy to train. GANs have better performance for high dimensions, and they are also difficult to optimize because of the unstable training dynamics. Except for a few situations, GANs cannot be done with inference. The applications of GANs include the following: generating realistic samples like artwork, generating inputs that expand the small data sets, font generation, image imprinting, super resolution, and the list goes on and on. So let's see what is really going on behind the scenes of the GANs. GANs have two neural networks against each other, the generator and the discriminator. The generator tries hard to mimic the expected samples, but it only receives noise. It tries to change the noise so that it looks like the real samples. So the generator creates fake art. The discriminator acts like an art critic. It has to predict whether its input samples are real or fake, like a critic. The generator is trained to generate realistic data and fool the discriminator, and the discriminator is trained to predict the data originality with high accuracy. The fight between these two networks improves their knowledge, which leads to the success of the generator. So let's see what is going on mathematically. The generator and the discriminator are modeled by neural network. A neural network, G of Z and theta 1, tries to map the input Z to the desired samples X. The input Z is the noise. A neural network D of X and theta 2 outputs the probability that the data came from the real dataset. Keep in mind that G is the generator and D is the discriminator. So D is trained by maximizing the probability when it is fed by the real data D of X, while minimizing probability when it is fed by the fake data called D of G of Z. The generator G of Z and theta 1 is trained by maximizing a D of G of Z. After several steps, both networks reach equilibrium point where they cannot improve any further. The formula of min-max optimization is given here. As you can see, this is the formula. The training algorithm of a GAN is given here. We consider a specific number of iterations, and for all training mini batches, we go through all iterations. In each iteration, we sample mini batch of M noise samples from noise prior P of Z. We must sample mini batch of M noise samples from real data from P of X. We must update the discriminator by ascending its stochastic gradient, as you can see here in the first formula. Then for all iterations, after all of the iterations are done, for each mini batch, we must sample mini batch of M noise samples from the noise prior P of Z and update the generator by ascending its stochastic gradient as the second formula suggests. The parameters are already defined in the previous slides. This simple image shows the main architecture of a GAN with a generator which gets the random noises and the discriminator which receives the training set and the fake images and decides whether its input are fake or real.